Welcome to the Deep Dive, your shortcut to being genuinely well-informed. We take the most impactful insights from, well, a whole stack of sources and distill them down into a fascinating conversation. Today, we're plunging into a topic that's not just generating buzz, it's actually reshaping our digital future. Agentic AI. We're not talking about AI that simply answers your questions anymore, not just chatbots. We're exploring a world where AI perceives, plans, acts, learns on its own, and even collaborates. It's a pretty big shift. We're going to pull back the curtain on the underlying architecture and the cutting-edge frameworks that are making this profound shift possible. Get ready to go deep.
And we are incredibly excited to guide you through this special deep dive. We're drawing directly from the recent Agentic AI Summit that just happened at UC Berkeley. This wasn't just another conference, It felt like a truly unique gathering. Leading minds from academia, from industry, all converging. And they were all there to discuss the profound and rapidly approaching future of AI agents. What makes this event particularly significant, I think, is that it was hosted by UC Berkeley's Responsible Decentralized Intelligence Center. RDI, they call it. RDI itself is this really interesting innovation hub. It's nestled within the university's brand new College of Computing, Data Science, and Society, which remarkably is the first new college established at Berkeley since the 1960s. So a big deal in itself. RDI's mission is pretty ambitious and critical too. They want to advance science and tech right at the intersection of responsible innovation, decentralization, and AI. And the core goal really is making these powerful capabilities universally accessible. They pursue this through these unique pillars, spanning deep research, impactful education, fostering a vibrant community, and also nurturing entrepreneurship. The sheer scale of this summit alone, it really speaks volumes about the interest and momentum behind agentic AI. We saw over 2,000 attendees participating in person.
Wow.
Yeah, and an additional 10,000 joining online from around the globe. And the event itself, it built upon an existing agent MOOC community. That's a massive open online course that already boasts over 25,000 global learners. Huge community.
Incredible reach.
Absolutely. So our mission today is clear. We want to extract the most important, most practical nuggets of knowledge about what truly powers these intelligent systems. We'll take you right from the raw silicon all the way up through the most complex software frameworks.
Okay, let's unpack this then. If we're talking about AI agents that can perceive their environment, formulate complex plans, and then actually execute those plans, take real-world actions, how do we even begin to build something like that?
Yeah.
It simply has to start at the absolute foundation, right?
Yeah.
It's the hardware, the fundamental stuff that ignites this entire revolution.
Absolutely. You have to start there. Think of it like this. Deep learning, at its very core, it needs three essential components to truly take off. Bill Daly, Nvidia's chief scientist, he frames it beautifully using an analogy of air, fuel, and spark. The air, in this analogy, refers to the algorithms. And surprisingly, maybe, core concepts like deep neural networks, backpropagation. They've actually been around since the 1980s.
Really? Since the 80s?
Yeah, core ideas. The fuel is data. That really started becoming abundant and accessible in the early 2000s, especially with large-scale data sets like ImageNet. But the critical missing ingredient, the spark, that fast enough hardware capable of processing these algorithms on these huge amounts of data, that was only truly provided by GPUs. It wasn't until GPUs delivered that spark that we could genuinely ignite this powerful mixture and finally kick off the AI revolution we're witnessing today.
So the hardware was the final piece of the puzzle, the catalyst.
Exactly. And to give you a concrete example of what these advanced agents are capable of now, let's look at a case study Nvidia highlighted. They talked about an agent named Eliante. It's designed to act very much like a second-year graduate student specializing in computational chemistry.
Okay, so a pretty specific role.
Very specific. You can pose a highly complex scientific question to it. Something like, what is the activation energy of caffeine? Eliante doesn't just, pull a pre-computed answer from some static database. No. Instead, it leverages this sophisticated hierarchy of multiple LLM-powered agents. Each agent in this hierarchy is essentially an LLM with its own internal state, some fine-tuning for specific tasks, and a very precise task prompt.
So it's like a team of specialized AIs.
Precisely. These specialized agents then work together. One might figure out how to generate the molecule's geometry, another will optimize that geometry. Then a third submits a job to a powerful supercomputer to run a density functional theory computation, the actual quantum chemistry calculation. And finally, a post-processing agent interprets that raw data to give you the precise, actionable answer.
That's incredible. It's actually doing the science.
It is. And what's absolutely crucial here, something Bill Daly really emphasized, is the indispensable role of tools. LINT uses complex quantum chemistry simulations, sure, but a tool can be as simple as a basic calculator. You are far better off, for instance, coupling even a 1 billion parameter LLM with a calculator for numerical stuff than attempting to get a trillion parameter model to do complex math purely through language.
Right. Let the model do the language and reasoning, let the tool do the calculation. Makes sense.
Exactly. This potent combination in LLM with internal state, memory, a defined policy for action, and access to a suite of external tools, that's what makes these agentic systems so incredibly effective and powerful.
That's truly remarkable. It's not just retrieving data, it's performing actual complex scientific computation. I imagine that kind of capability opens up entirely new frontiers for research, doesn't it?
Oh, absolutely.
And what's fascinating here is that this isn't just about making individual chips faster. It's about meeting an exponential growth in compute demand. That growth sounds almost unprecedented in its scale and speed.
Indeed. The growth in compute demand has been absolutely staggering. It's almost hard to believe, actually. Historically, for early computer vision models like AlexNet, the demand for compute power grew at about 3x per year.
Which is already pretty fast.
It is.
Yeah.
Even that's a significant engineering challenge to keep up with. But since 2017, with the breakthrough of transformer-based models, the attention is all you need paper, this growth rate has absolutely exploded. We're talking an unsustainable 16x per year.
16 times. Every year.
Every single year. Think about that.
Yeah.
So Nvidia, as a primary provider of this foundational hardware, they feel this immense responsibility. Because in many ways, the very advancement of AI models and what they can achieve is directly gated by the performance of the hardware available to train them. They face constant, immense pressure each generation, not just to increase single GPU performance, but also to dramatically improve the ability to scale up to truly massive multi-GPU clusters.
So how did they keep up? What did that evolution look like on the chip level?
Well, consider the incredible evolution of NVIDIA's GPUs, specifically engineered for deep learning over the past, say, 12 years. It all started with the Kepler architecture. Interestingly, Kepler wasn't even designed for AI originally.
Oh, really?
Yeah, it was focused on graphics and high-performance scientific computing, using 32-bit and 64-bit floating point precision, which is actually overkill for deep learning's needs. But an internal project back in late 2010, attempting to replicate Andrew Ng's groundbreaking experiment training neural nets to find cats on the internet using GPUs, that fundamentally convinced them AI was the undeniable future.
The famous cat experiment.
That's the one. So by the subsequent Maxwell and Pascal generations, they began to introduce optimizations specifically for AI, things like 16-bit floating point, or FP16, and specialized dot product instructions. The next truly monumental leap came with the Volta generation. This is where they introduced what they called tensor cores.
Tensor cores, right.
While the marketing team gave them that name, they fundamentally perform half-precision matrix, multiply accumulate operations way more efficiently by amortizing instruction overhead. It was a game changer. Then came Ampere, which added sparsity awareness, Hopper, bringing in FP8, and most recently Blackwell, pushing even further to FP4.
FP4, down from FP32.
Exactly. This relentless drive towards lower precision number representation, moving from the more traditional FP32 down to FP4, has alone yielded a massive 32x performance gain. It's a foundational shift in how calculations are performed right there on the silicon.
So that's a remarkable jump, 32x, just from changing the number format. What does this all mean for the silicon itself, and how is this staggering performance actually achieved on the chip? Because that 32x gain is just one piece of the puzzle, right? There must be more.
Precisely. It's quite fascinating because historically, with CPUs, the bulk of performance gains came primarily from process technology, shrinking transistors according to Moore's law. But that rapid pace of process scaling has actually, slowed down for about 20 years now, since Dennard scaling effectively ended around 2005. Over this entire period we're discussing, from Kepler to Blackwell, process technology alone has only contributed about a 3x gain to the total performance improvement.
Only 3x from shrinking transistors, but you said the total was huge.
Exactly.
Yeah.
Yet we've seen a total improvement of approximately 4,000x.
4,000 times. So where did the other 1,300x come from?
Okay, good question. So the biggest single gain, as we just discussed, came from that shift in number representation, going from SP32 to FP4 yields that direct 32x boost. The next largest gain, contributing about 12.5x, comes from using complex instructions.
Complex instructions, what does that mean practically?
Let me give you a more intuitive example to illustrate this. Imagine a simple half-precision floating point multiply-add operation, a basic calculation. It might cost about 1.5 picojoules of energy to actually do the math.
Okay, tiny amount of energy.
Tiny. But the overhead fetching the instruction, decoding it, retrieving the numbers, storing the result back, that costs a staggering 30 picojoules for that single instruction.
Wait, 30 picojoules just for overhead compared to 1.5 for the math?
Yep. That's a 2,000% overhead. It's like, I don't know, a huge corporation spending 20 times more on admin than on actual productive work. It's wildly inefficient. By introducing dot product instructions, that overhead dropped to a still significant 5x. But with matrix multiply instructions, those tensor cores we mentioned, the overhead for a single instruction that performs many operations is now just 22%. And in today's GPUs, it's pushed even lower, maybe around 11%. This radical reduction in instruction overhead is absolutely critical, not just for raw speed, but also for energy efficiency. It's huge.
That makes so much sense. Reducing the bureaucracy of the calculation.
Exactly. Another major factor for performance, especially for the largest AI models, is multi-GPU scaling. We've gone from training AlexNet on just 2 GPUs maybe a decade ago to typical training clusters today employing 100,000 GPUs for a single job.
100,000 GPUs for one training run?
For one run.
Yeah.
And there are 2 primary ways to parallelize this. First, there's data parallelism, which is relatively straightforward. You split batches of data across different GPUs, each trains on a portion. Then there's model parallelism, which is much harder but absolutely necessary for training these truly enormous models. This involves techniques like pipeline parallelism. Think of it like an assembly line where each GPU processes a different stage of the model's computation, passing its output to the next. And then there's tensor parallelism, which is more like a single massive calculation, like a huge matrix multiplication within one layer, being broken into smaller parts and handled simultaneously by multiple GPUs working side by side.
Okay, so complex ways to split the work across thousands of chips.
Very complex. And finally, we absolutely cannot overlook the critical role of software optimization. Independent assessments like the MLPerf benchmarks have shown a remarkable 2.5x performance improvement on the exact same hardware in just 6 months, purely due to software optimizations.
Wow, same chips, just better software, 2.5x faster.
Exactly. This vividly highlights how absolutely critical, efficient, well-designed software is for realizing the full theoretical performance of the underlying hardware. It's not just about the silicon, it's about making that silicon dance.
That's a truly holistic approach to performance then. Hardware, architecture, parallelism, software, all working together. Now, if we connect this back to agents specifically, where do they push the boundaries for hardware demands? It seems like they introduce entirely new types of workloads, different from just training or basic inference.
They absolutely do. When we talk about LM inference, using a trained model to generate output, there are 2 distinct phases. And agents stress one of them far more than traditional chatbots. The first is the pre-fill phase. This is when you process the entire prompt you feed into the model. Your input, the system prompt, any documents retrieved via REA, retrieval augmented generation. The goal here is to produce the very first output token and populate something called the KV cache. This phase is highly parallel and typically limited by the math capabilities of the hardware.
Okay, processing the input prompt.
Right. The decode phase, however, is where it gets particularly tricky and demanding for agents. This is an autoregressive phase. Each new token generated depends on the preceding one. You essentially have to read the entire model, or large parts of it, for each and every token you generate. This makes it incredibly bandwidth and latency sensitive.
So generating the response word by word, essentially.
Exactly. And agentic models, with their complex chain of thought, tree of thought processes, they heavily stress this decode phase. Consider this. For every single token the user actually sees, an agent might process 10 times more internal tokens as it performs multiple reasoning steps, self-correction, calls tools.
10 times more work behind the scenes for every word we see.
Easily. So if you want to deliver, say, 100 tokens per second to a human user for a smooth experience, your hardware needs to be executing at a rate of 1,000 internal tokens per second. This drives very specific and fundamentally different demands for hardware compared to just the prefill phase. Much more focus on latency and bandwidth. Furthermore, the world of AI models is constantly evolving. New approaches like mixture of experts, or MOE, are emerging daily.
Mixture of experts? What's that?
So MOE models are kind of like having an ensemble of specialized submodels, like little experts inside the big model. The AI intelligently routes different parts of a problem to the most relevant expert submodel, make them incredibly efficient for certain tasks. This constant innovation requires highly programmable architectures. You simply can't hardwire your designs, build application-specific integrated circuits or ASICs for today's models, because they'll be obsolete almost immediately. You need that flexibility.
Got it. So it's not just about what's happening exclusively in these colossal data centers then. Agents are clearly going to be ubiquitous, affecting a full spectrum of devices, from the cloud right down to the edge.
That's AMD's core vision, exactly. And it's something they articulate very clearly. We're fundamentally entering the agentic system era. This is a paradigm shift where AI is designed not just to generate text or images, but to perceive its environment, formulate sophisticated plans, and then act autonomously, directly mimicking, the complex cognitive functions of the human brain beyond just generation or conversation. And to achieve this, it absolutely requires a full spectrum of hardware. In the cloud, sure, you'll have powerful GPUs acting as the big brains for frontier LLMs, handling the most demanding tasks. But then you have this vast array of endpoint devices, like our everyday laptops now equipped with NPUs, neural processing units.
Right, NPUs are showing up everywhere now.
They are. And they're powering local AI features like Copilot, plus live transcription, real-time translation right there on your device without needing the cloud. The explosive growth of AI at the edge, literally on devices closest to where data is generated and actions are taken, is particularly compelling. Think about autonomous cars. Subaru's EyeSight system for 3 generations now has been powered by an AMD Xilinx system on chip and SASE. It's meticulously running computer vision and now advanced AI algorithms to keep drivers safe.
So AI in my car's safety system.
Yep. In the medical field, Illumina uses AMD SoCs for incredibly fast genome analytics. They're accelerating the diagnosis of sick newborns from what used to take days down to mere minutes, literally saving lives by providing rapid critical insights.
That's incredible impact.
It is. Even the scientific frontier benefits. CERN's Large Hadron Collider uses small AMD SoCs to gather and process vast amounts of data from high-speed proton collisions, enabling discoveries like the Higgs boson. And perhaps the most fun and futuristic example. One of these very AI chips is currently on Mars, running around in the Perseverance rover.
An AI chip on Mars.
Yeah. Which is, in essence, a sophisticated self-driving car on other planet, navigating and performing scientific experiments autonomously. So it's not just about the big brains in the data center. The edge and endpoint use cases are exploding, and agentic AI will leverage all of it, seamlessly interconnected.
That's incredible to imagine AI operating autonomously on Mars. And what does this all mean for how these different pieces across the spectrum talk to each other? The connectivity and communication must be incredibly important if we're moving towards this truly distributed AI.
It's absolutely crucial. All these devices, from the most powerful cloud servers to the smallest edge devices, they're designed to be fully connected, constantly discovering and communicating with each other. This isn't just, a theoretical concept or a nice-to-have feature. It's fundamental to how truly agentic systems will operate. We're moving towards an open and collaborative AI era, which is precisely why AMD's entire software stack, from the lowest levels up, is built on open-source principles, including significant contributions to projects like AI Triton.
So open source is key for that connection.
Vital. This open approach is vital for enabling the seamless communication, interoperability, and collective improvement required across this vast distributed network of AI-powered devices. Without open standards, this kind of expansive ecosystem simply wouldn't be possible.
This raises an important question then. What if we think about designing for agents not just as engineering machines, but almost like humans building a society? What kind of society or infrastructure do we need to build for them, maybe drawing lessons from how human society itself is structured?
That's a fantastic analogy, actually. And it's precisely the thoughtful perspective that Lambda Compute brings to the table. They really lean into that. They start by looking at the core infrastructure needs of human society, and then draw direct parallels to what intelligent agents will require. First, consider the most fundamental utilities. Data is the essential fuel, right? And compute is the electricity that powers everything. While we will undoubtedly need to build more data centers, more power stations to keep up with demand, efficiency is absolutely paramount.
Yeah.
We can't just keep scaling indefinitely. We need not just general power efficiency, more flow per watt of compute, but there's also a significant paradigm shift emerging. It's increasingly not just about making compute more efficient, but making data movement dramatically more efficient.
Moving the data around becomes the bottleneck.
Exactly. LLMs, especially with their incredibly long context windows, they constantly need to fetch vast amounts of data from different memory hierarchies across different chips, sometimes even from storage disks. This presents a massive, often overlooked data movement bottleneck. For cloud solutions, operational efficiency is also a critical utility, providing cost-effective and elastic resource provisioning, enabling the use of federated resources spread across different regions and clouds, and offering managed experiences on top of orchestrators like Slurm or Kubernetes to simplify deployment and management. You need that operational layer.
Okay, so managing the power and fuel efficiently. It also sounds like we need to make sure agents have the right information diet and can process it incredibly efficiently. It's not just about raw data, but about accessible and optimized data.
What's truly fascinating here is the relentless drive for data efficiency. That's a huge focus. The ideal scenario is that all relevant data should reside in one accessible place, right? With incredibly cheap storage and lightning-fast query capabilities. This data also needs to support multimodal formats, meaning it can handle not just text, but images, audio, video, sensor data, you name it. And it needs to be seamlessly integrated with existing AML and business intelligence systems. You can't have data silos.
Right, break down the silos.
Exactly. Now, for model efficiency, the focus shifts to empowering users to build their own specialized models with their own proprietary data. We need intelligent model routing to connect the right, most appropriate model to the right task. You avoid the computational waste of using an overly complex, massive model for a simple problem. A smaller, highly specialized model, when properly equipped with the right tools, is often far more efficient and effective than a huge monolithic model trying to do everything internally.
Use the right tool for the job, basically, even if the tool is an AI model.
And what about the soft skills, or perhaps the education system for agents? How do they learn to communicate and collaborate, mirroring the nuances of human interactions? Do we need to teach them manners?
Well, maybe not manners exactly, but it truly is all about communication and collaboration, much like in a human society. Good communication for both humans and agents comes from a good user experience. For us humans, we need sub-200 millisecond latency for truly good interactive experiences. Our attention spans start to wander if we have to wait more than a few seconds.
Really? Impatient.
We are. And we're also not inherently great at multitasking in the same way a machine is. Agents, on the other hand, can run many jobs in parallel. They're incredibly adept at multitasking. So sometimes the time to last token, when the complete answer is delivered, might actually be more important for them than the time to first token that we humans crave for responsiveness. Agents also process and need to remember vast amounts of information within a single session, so high memory capacity and high memory bandwidth are absolutely crucial for their effectiveness. They need to hold a lot in their heads.
Okay, so they need big, fast memory. And what about interacting with the world?
Right. We also desperately need better user interfaces, not just for humans interacting with agents, but interfaces for agents themselves. Natural language is currently the primary interface, enabling agents to connect to various tools, which is powerful. But as agents begin to step more actively into the real world, they'll require true multimodal model context protocol, or MCP, meaning the fundamental ability to see, hear, and sense the real world around them in order to take meaningful actions. They need more senses than just text.
So they need eyes and ears, essentially.
Essentially, yes. And finally, just as human society has robust workforce development systems, schools, training programs, agents need robust platforms to train, evaluate, and continuously improve them. Lambda Compute emphasizes that evaluation is probably one of the most challenging and frankly underrated steps in this entire process.
How do you even measure if an agent is good?
Exactly. Static leaderboards, while useful as initial guardrails or for comparing models, they're certainly not the ultimate destination, not sufficient. Real-world project embodiment and evaluation are critical to truly assessing an agent's capability. This involves not just technical performance, but also something they call cultural fitness. Does it fit within the organization's norms? And of course, compliance. It's relatively easier to integrate agents in vibe-setting tasks like coding assistance or research brainstorming. However, as they integrate into core business processes touching internal sensitive data, utilizing internal tools, generating external-facing services, robust security, safety, and compliance mechanisms become absolutely paramount. You can't mess that up.
The stakes get much higher.
Much higher. And this leads to a provocative thought Lambda Compute left us with, something for you to consider. If tokens are rapidly becoming the currency for AI, and that currency has been dramatically deflating in value over the past year due to efficiency gains and competition, what are the long-term implications for the sustainability of this AI economy? Who are the banks in this new financial landscape? And could human feedback itself, our collective preferences, our interactions, could that somehow become a new form of token? Or even a valuable currency for agents, shaping their evolution and value?
Wow, human feedback as currency. That's a truly fascinating and indeed provocative thought, especially about the value of our clicks and preferences in this new AI economy. It makes you wonder about the very fabric of this emerging digital society. And speaking of foundational aspects, as we build these increasingly complex agentic systems, one word keeps coming up that's absolutely critical to their real-world utility: reliability. But achieving it for AI is proving uniquely challenging, isn't it?
It absolutely is. And this is a core focus of Jan Stoica's keynote on reliability. It's from Anyscale in UC Berkeley. He began by defining reliability for traditional systems: their ability to function consistently under stated conditions for a specified period. It encompasses crucial attributes like accuracy, correctness, consistency, predictability, robustness, safety, the usual engineering stuff. The critical point he made, which resonated deeply, is that reliability is essential for AI's widespread success. Without it, the profound transformative impact everyone hopes for will remain incredibly difficult to achieve. We just won't trust it enough.
Makes sense. You need to trust it works.
Exactly. And he highlighted precisely why it's so much harder to achieve reliability for AI agents compared to traditional software. Traditional software components typically have clear, explicit specifications. This allows engineers to perform white box testing, where they can examine the internal logic, debug down to the specific line of code when an error occurs. LLMs, however, are fundamentally black boxes. It's incredibly difficult to even know when an error has occurred, let alone how to pinpoint and fix it at a code level within the model's vast, opaque neural network.
Right, you can't just look inside and see the bug easily.
Not at all. It's like trying to debug a complex program where you can only see the inputs and outputs, and you have to guess what went wrong internally without any visibility. This opacity is a monumental hurdle for reliability.
That's a crucial point about reliability, and it seems like a core challenge that we're dealing with these black boxes. So how exactly are platforms like Chatbot Arena helping to shine a light into that black box? And what unexpected insights are you gaining from human interaction that traditional testing simply can't provide?
That's right. Chatbot Arena, which used to be called LM Arena, is a powerful and very practical real-world approach to human evaluation. It's managed by LMSYS. It's a classic human-in-the-loop model. Users interact with anonymized, randomized LLMs. They don't know which model they're talking to. They ask questions. Then, crucially, they provide preferences for which answer they found to be better, Model A or Model B.
So direct human judgment.
Exactly. Jan Stoica broke down human preference into two critical components: substance and style. Substance, as you might expect, is about accuracy and factuality. Is the generated result correct? Does it provide the right information? Style, on the other hand, is about how the output looks and if presented, its tone, its formatting, the UI UX around it.
Style seems less important than substance, maybe?
You might think so, but he argued convincingly that style is extremely important because it profoundly dictates how reliably humans interact with these systems. Much like a well-designed user interface makes traditional software more effective and intuitive, good presentation and clear communication help people effectively ingest, retain, and process the information provided by an AI. If it's confusing or poorly presented, people might misuse the information even if it's technically correct.
Ah, I see. So style affects how reliably the human uses the AI.
Precisely. He shared concrete examples from their analysis. In a text-to-video demo, users voted on their preference for various generated videos. For text-based responses, they found that answer length was a dominant preference factor. Longer answers often preferred because they provide more detail and context, seem more thorough. Markdown and proper formatting were also very important indicators of quality and preference, makes it easier to read. But here's the truly surprising finding, which goes against some popular beliefs, especially maybe from model trainers. The number of emojis in an AI's response had a consistent negative correlation with user preference.
Wait, fewer emojis are better? I thought people liked friendly AI.
It seems that way. While a few emojis might add flair, an excessive use actually detracts from perceived reliability and professionalism for many users. Maybe it feels less serious or trustworthy. Chatbot Arena has had a massive impact, becoming a critical barometer for model quality. It boasts over 3 million monthly users, facilitates 10 million monthly conversations, and processes over 1 million monthly votes across more than 700 different models.
That's huge scale for human feedback.
It's an incredible crowdsourced reliability assessment.
That's a fascinating insight about emojis. But beyond just user preference for a single response, What's truly going wrong inside these more complex multi-agent systems? It seems like there's a deeper systemic issue that goes beyond just the quality of a single LLM output. Where do these multi-agent systems truly break down?
Absolutely. This is precisely the question that motivated the creation of the Multi-Agent System Failures Taxonomy, or MAS project, another LMSYS initiative. This project was born from the stark observation that many agents fail over 50% of the time on hard, complex benchmarks. Just not reliable enough yet.
Over half the time they fail.
On the hard stuff, yeah. MS' ambitious goal is to systematically identify, classify, and analyze the specific reasons for these failures. They embarked on this intensive process, manually inspecting over 150 traces of agent interactions to build their initial taxonomy, really digging into the logs. Then they cleverly designed an LLM judge pipeline that remarkably agreed with human evaluation 95% of the time on over 1,000 traces. This allowed them to scale their analysis significantly. And this rich data set, the taxonomy, thankfully, it's all open source for the community to build on.
So what did they find? What are the main ways these agent teams fail?
They identified three main overarching failure categories. 1. Specification issues. This occurs when agents simply fail to understand or properly obey the task specifications they're given. Or sometimes they even fail to understand their own defined roles within a larger multi-agent team.
They don't understand the instructions.
Or their job description, basically. An example they shared came from ChatDev, a framework where different agents, like a CEO, a Chief Product Officer, CPO, engineers cooperate to build software. In one instance, the CEO agent clearly communicates what it wants to the CPO agent. But the CPO agent, instead of continuing the development process, just stops the conversation entirely, flat out stops.
Just quits.
Yeah, which highlights fundamental design limitations in how the agentic system interprets its own internal directives and the overall goal. It didn't follow the plan. 2. Inter-agent misalignments. This category covers critical information loss or outright confusion that occurs during conversations or interactions between different agents.
Like miscommunication in a human team.
Exactly like that. They gave a compelling, almost frustrating example. A supervisor agent asks a phone agent to send a WhatsApp message. This requires the phone agent to log into a messaging service first. During the login attempt, the phone agent confuses an email address for a phone number. Simple mistake, right?
Yeah, it happens.
But, crucially, this specific error, this misinterpretation, is not propagated back up to the supervisor agent. The supervisor has no idea what went wrong or why the message wasn't sent. So the supervisor agent can't diagnose or fix the problem. This points to a profound need for what they termed deeper social reasoning in agents, the ability to understand context, infer intent, and communicate failures effectively across a team.
They need better teamwork skills.
In a sense, yes.
Yeah.
3. Task verification issues. This category highlights a significant weakness in current agent verifiers, the part of the system that checks if the work was done correctly. In a chess program example, the agent might fail to use standard chess notation or even allow illegal moves like pawns moving backward.
Pawns moving backward? That's not chess.
Right. Yet the programmed verifier still confidently declares the generated chess program good. These verifiers frequently provide insufficient or even misleading feedback to the agent. This prevents the agent from truly learning from its mistakes and correcting its behavior. Bad feedback loop.
So the checker isn't checking properly.
Essentially. Jan Stoka concluded with a profound implication for the entire field. Reliability in AI, particularly for automated decision-making where there isn't a human constantly in the loop, absolutely demands explicit, unambiguous specifications, clear instructions. This is something that is largely missing from today's black box LLMs, and it represents a strong call to learn from other more mature engineering disciplines like civil engineering, aerospace engineering, that have long relied on precise, clear specifications to build trusted, reliable systems. We need that rigor.
That really underscores how complex reliability is in these systems. So if reliability is such a challenge, how do we get agents to actually learn and get better, especially with real-world tasks where a mistake can be costly, slow, or even dangerous? How do they improve?
That brings us to Matej Zaharia's groundbreaking work. Matej Yuria, actually, from Databricks in Stanford, working on the DSPY framework. He talked about reflective optimization. He drew a sharp contrast with traditional machine learning methods, like weight updates via gradient descent. Those methods require a truly massive number of examples to learn. We're talking trillions of tokens for pre-training a large language model, or hundreds of thousands of rollouts, simulated experiments, for reinforcement learning.
Just huge amounts of data or trials.
Exactly. This approach is profoundly sample inefficient, meaning it requires an exorbitant amount of data or experiences, and it's far too slow for real-world tasks. especially when those experiments might take hours, days, or even longer, not mere minutes, to yield a result. You simply cannot run 100,000 physical world experiments to teach an agent something without incurring prohibitive costs or time delays. It's just not practical.
Okay, so traditional learning is too slow and needs too much data for complex agent tasks. Here's where it gets really interesting then. They're teaching AI to learn from its mistakes in a surprisingly human-like way, almost like self-reflection, right? Where a system can look back at its actions and figure out what went wrong.
Exactly. The core innovation here is reflective optimization. But it operates in what they call prompt space, not model weight space. Instead of just getting a simple O1 success-fail signal, an LLM is prompted to look at its entire trajectory. That means all the commands it issued, all the outputs it received, every message it exchanged with tools or other agents, the whole history. It then reflects on what went wrong, systematically integrating all that detailed information to diagnose the root cause of the issue.
So it reads its own log files and thinks about them.
Pretty much. And the truly crucial part is that this reflection is then used to update a prompt, not the underlying model weights. The LLM essentially writes down notes for itself, or new instructions, maybe refined examples, for future attempts at similar tasks. It modifies its own operating manual.
So it learns by editing its instructions, not retraining the whole brain.
Exactly. This is an absolute game changer for sample efficiency because, unlike those infinitesimal weight changes in traditional training, even one major mistake can lead to a complete avoidance of that specific error in the future. One bad experience can teach a big lesson. That kind of rapid, high-level learning is simply not possible with traditional low-level weight adjustments. They developed an evolutionary algorithm for prompts called GEPA, stands for Genetic Programming for Prompt Augmentation. Or maybe genetic burrito, the whimsical name stuck.
Burrito.
Yeah. The results they presented are incredibly compelling. GEPA vastly outperforms traditional reinforcement learning methods like GRPO on complex tasks such as multi-hop search, like the Hotpot QA benchmark. It learns significantly faster, requiring only tens of rollouts compared to GRPO's 25,000 rollouts to achieve similar or even better performance.
Tens versus 25,000, that's orders of magnitude faster learning.
Huge difference. It even managed to outperform models specifically specialized for these tasks. And what GEPA learns to generate are these highly detailed, tailored prompts. They include specific examples, warnings about common pitfalls. It demonstrates this ability to write prompts that a human might not even conceive of. It's learning prompt engineering automatically.
So the AI is writing better prompts for itself than humans could.
In some cases, yes. They've successfully applied this approach to closed-source models, like solving math problems with GPT 4.1, and even outperforming human-written agentic plus ARG pipelines for understanding new hardware documentation. This truly suggests that these higher-level prompt updates, driven by the model's increasing ability to reflect and follow instructions, could very well be the weight updates of the future, making AI learning far more efficient and practical for real-world complex applications.
That's a mind-bending idea, prompt updates as the new weight updates. From this grand vision of how agents learn through self-reflection, let's step back and ask a big question. Have agents truly arrived in the mainstream? It was often billed as the year of agents, but where are we really in terms of widespread adoption and impact?
Sherwin Wu from OpenAI offered a remarkably frank and insightful retrospective on the year of agents. He works on their applied AI team. He acknowledged the rapid succession of significant product launches from OpenAI itself, things like Operator, Deep Research, GPT 4.3, Codex for Coding, the HGPT agent. A lot came out quickly.
Yeah, felt like something new every week for a while there.
It did. But despite this impressive rollout, his candid assessment was that agents haven't quite hit the mainstream yet, not in the way maybe some expected. He drew a compelling analogy to the unfulfilled, long-standing promise of the flying car, a vision that continues to capture our imagination but has yet to become an everyday reality for the average person.
Still waiting for my flying car. And maybe my fully autonomous AI agent.
Kind of feels that way. Crucially, he took the opportunity to directly debunk two very common misconceptions about why agents aren't yet widely adopted. First, it's not due to a lack of demand. He emphasized that usage absolutely explodes the moment an agent works effectively. He cited Deep Research, which allows agents to autonomously conduct complex web research, and coding agents like Cursor, which assists programmers, as prime examples. People are using them heavily when they work.
So people want them if they work well.
Definitely. People genuinely want to save time and automate tedious tasks. The appetite is clearly there. 2. Second, and perhaps more surprisingly, it's not due to a lack of underlying model intelligence. He spoke about what he called a capability overhang, where models like GPT 4.3 are already at a level of intelligence that often surpasses human capability for complex, demanding tasks. A fine-tuned version of GPT 4.3 for deep research is, in his own words, straight up better than me at researching complex tasks.
Better than the expert developer. Wow.
Yeah, the intelligence is there, the problem lies elsewhere.
So, what does this all mean? If it's not a question of demand or core intelligence, what are the primary practical reasons blocking mainstream agent adoption, according to OpenAI's first-hand insights? It sounds like the challenges are more about deployment and integration, maybe the practical stuff.
You're exactly right. Sherwin identified 4 core deployment-related blockers that are holding agents back from widespread adoption. 1. Connectors. The fundamental ecosystem of tools and connections is simply not yet mature enough for agents to effectively interact with the real world, especially the digital world of enterprise systems. He analogized it to a brilliant person sitting at a desk with a powerful computer, but with no access to data, no internet connection, no tools. Pretty useless, right?
Right. Smart, but isolated.
Exactly. While important standards like MCP, Model Context Protocol, are emerging to help agents communicate, the vast amount of internal organizational data, estimated to be 4 times larger than public data by the end of the year, remained a daunting challenge to connect agents to. All the proprietary databases, internal dashboards, enterprise apps, that's where a lot of value lies. 2. Lack of generalizability. Agent tool use is still too often tightly coupled to specific, predefined tools. It's brittle. For instance, deep research excels at web search, but might struggle dramatically when asked to use a custom internal financial reporting tool it hasn't seen before. An Apple paper was cited that vividly illustrated this problem, showing significant performance drops when agents' tools were even slightly perturbed or changed.
So they aren't good at adapting to new tools on the fly.
Not yet, generally. The argument is that we don't necessarily need agents to be masters of every tool. Instead, maybe we need tools specifically tailored for the model, suggesting a paradigm of simple, specialized tools combined with a very smart, generalist model that knows how to use those simple tools well. 3. Difficulty of creating agents. There's a surprisingly high activation energy due to the sheer complexity involved in building truly robust agents. It's just hard to do well. Consider this. OpenAI's own practical guide to building agents is a daunting 32 pages long.
32 pages just for the guide. Oof.
Yeah. This inherent complexity significantly hinders unlocking the full economic value of agents across a wide range of tasks and industries because it requires specialized expertise that is simply not widely available yet. It's still too much of an art. 4. Cost. Running agents is still not cheap, especially with long inference jobs, multi-step chain of thought processes, and the use of ensembling running multiple agents or models and combining their results for better accuracy. That all adds up.
All that thinking costs money.
It does. A concrete example given was GPT 4.3 running at 40 tokens per second, which could cost around $27 per month if you're only counting output tokens, with input tokens cached. You're one user, maybe.
Okay, not free.
Not free. However, there is genuinely good news on this front. Prices are dropping dramatically, at an astonishing rate of 900x per year, according to their estimates.
900 times per year cheaper? How is that even possible?
It's driven by a combination of factors.
Yeah.
Model distillation making smaller, efficient versions of large models, clever inference tricks in software, continuous hardware optimizations like we discussed, and just intense price battles among AI providers. This means these costs could very soon drop to mere pennies, making widespread adoption far more feasible. Cost might become a non-issue relatively soon.
Okay, so those are the blockers. Connectors, generalizability, difficulty, and cost. But the cost is dropping fast. Imagine a world where these critical blockers are methodically removed one by one. What's the truly optimistic, even transformative vision for agentic AI then?
The vision is nothing short of transformative, really. We could see a truly personalized AI assistant for every single human being. Anticipating needs, managing tasks effortlessly, knowing your context. We envision context-aware AI becoming the intelligence center of every business, automating complex workflows, providing real-time insights, maybe running entire departments, and ultimately, millions, even billions of mini agents could seamlessly fill the gaps in countless workflows, orchestrating tasks between different software, making our digital lives far more productive, and fundamentally changing how we interact with technology and information. It's a future where AI isn't just a tool you consciously use, but a ubiquitous, intelligent fabric woven into everything.
A pervasive intelligence layer. Building on that expansive vision, let's hear from other leaders who are actively shaping the future of agentic AI, from broad conceptual frameworks to concrete, practical tools they're developing right now. What else did we hear at the summit?
Right, there were several other key perspectives. First, we heard from Ankur Chang at Google DeepMind. He articulated this powerful dream of a digital companion that truly grows, learns, and collaborates with you over extended periods, not just task-based, but a real companion. He highlighted key advancements across 3 areas. On the interface front, AI is rapidly gaining senses, essentially sight and sound. Capabilities like Gemini Live, which can use your phone camera to literally see the world you're interacting with during a conversation and speak back in real time.
Seen through my phone camera.
Yeah, and it can also see your screen and trigger actions on it. This dramatically narrows the gap between human intent and AI understanding. It can see what you see. Then there are evolving capabilities and actions. Coding assistants are increasingly acting as meta-powers that can self-improve, intelligently experiment with different solutions, learn from the outcomes, and even autonomously spawn new subagents to tackle specific programming challenges.
AI creating other AIs to help it code.
Pretty much. To truly realize this, Chang emphasized, we need robust cross-session reflection, persistent long-term memory for agents, and the ability for them to learn deeply through continuous interaction. Finally, he spoke of scale and collaboration. With groundbreaking frameworks like A2 and the new open-source project MassGen, they're orchestrating incredibly complex multi-agent teams in parallel. These agents can observe and refine each other's work recursively.
Like AI peer review.
Exactly. This recursive scaling has exponential potential, but it critically requires solving fundamental challenges like achieving consensus among agents, maintaining shared context across the team, and ensuring seamless interoperability across diverse agent types.
Okay, so DeepMind is focused on that collaborative learning companion vision. What about automating work?
That's where Jerry Liu of Llama Index offered his very practical perspective on automating knowledge work. He insightfully noted that current models, even the most advanced ones, are essentially blank slates. Even the best LLMs require users to meticulously supply prompts, select tools, provide relevant metadata. It's a lot of work for the human. He argued that the biggest barrier to unlocking AI's true value is actually the human's ability to use AI effectively, what he termed context engineering, getting the right info into the model.
So the human is the bottleneck.
Often, yes. To automate knowledge work efficiently, he stressed that it demands proper context combined with rigorous workflow engineering. Context and tools involve agent reasoning loops equipped with tools or MCP servers to access external information. But the current limitation is still the human's responsibility for precisely defining the input and setup. Workflow engineering, on the other hand, is about encoding repeatable patterns, defining a constrained series of steps with preset prompts, which then allows for repeatable use without constant, minute-by-minute human prompting. You automate the process.
Building reusable AI workflows.
Exactly. Frameworks like Llama Index are purpose-built to help standardize these complex agentic applications. He explained how MCP can go beyond just providing context. It can provide entire workflows as tools, truly offloading mental burden from the user by automating multi-step processes.
Makes sense. Standardizing the workflows. What about the open source angle?
Then, we heard a powerful call for open source and open standards from Matt White, representing both the PyTorch Foundation and Linux Foundation, a big voice in open source. He offered a provocative statement, positioning open models as eating open source, and then boldly declaring that open agents are fundamentally eating everything, basically the next big wave.
Open agents eating everything. Strong claim.
It is. He outlined what he considers the right way to do open source in this new AI era, focusing on solving real-world problems, constantly innovating, building strong communities, choosing appropriate licenses. He specifically mentioned the Linux Foundation's OpenMDW for models, which handles both code and data, and defining clear roadmaps with transparent community engagement. His agentic wish list was quite comprehensive, a critical need for universal alignment, standards, protocols, schemas across agents. We need common ways for them to talk. A much stronger focus on security, which he noted is currently largely absent in agent design. Big gap there.
Security is often an afterthought, unfortunately.
It often is. He also wished for building agentic functionality directly into the models themselves, citing the K2 initiative as an example, and vastly improving observability and tracing, as debugging complex agent workflows is currently incredibly difficult and opaque. We need better tools to see what they're doing.
So better standards, security, observability. Foundational needs. Did we see any concrete examples of open source agents?
Yes. Finally, Brad Axon from BlockGoose provided a compelling, practical example. He introduced Goose, which is Block's open-source AI agent designed for individuals.
Right.
Goose uses MCP as its core protocol to define its capabilities and extend its reach to various systems and applications. A key flexibility he highlighted is its ability to seamlessly switch between different models mid-conversation, leveraging the best model for a given task. For example, using Qwen 3 specifically for coding tasks, thereby always staying on the performance frontier.
Smart. Use the best brain for the job at hand.
Right. He stressed that embracing open source ensures long-term access, fosters collective improvement through community contributions, and encourages vibrant discussion and innovation. He then demonstrated an impressive use case. Goose, given access only to a database and a text editor, could generate a fully functional HTML dashboard from scratch.
Just from a database and a text editor.
Yeah. It showcased how combining relatively simple tools can enable surprisingly advanced and complex projects. He particularly highlighted Playwright, a web automation tool, which acts as an MCP server. This effectively gives the agent the ability to see and manipulate elements on a web page, creating a powerful feedback loop from the visual layer back into the agent's code. It could see the dashboard it was building.
Okay, let's try to unpack all of this. We've covered a vast amount of ground, journeying from the raw silicon powering these systems, through the intricate frameworks that orchestrate their behavior, and heard from the very leaders building the future. Let's synthesize some key insights from these expert panelists. What's truly unique and transformative about this agentic era? What classic problems in computing are kind of repeating themselves? And maybe where might the industry consensus be getting it wrong?
Okay, great questions. To synthesize the uniqueness of this agentic era, I think it's critical to understand it's not simply about generative AI in isolation. It's not just about making text or images. It's about building systems that generate many more tokens internally for reasoning, often with very long context, holding vast amounts of information, all while demanding very low latency and cost for real-time interaction. It's a different performance profile. It's fundamentally a full-spectrum challenge, like AMD said, spanning from cloud servers down to the smallest edge devices, with all these components designed to be fully connected and communicating seamlessly. And there's that distinct and crucial shift underway, from data being the old fuel that powered initial AI, to inference, the actual use of trained models, becoming the new engine driving value and innovation. How efficiently can we run these things?
Inference is the new bottleneck, the new focus.
Exactly. As for rhyming history in computing, well, several classic problems and enduring principles keep resurfacing in this new context. The fundamental importance of operational efficiency, elastic provisioning, load balancing remains absolutely critical. These are classic cloud computing problems, now applied to AI workloads. Fundamental programmability, like Nvidia's CUD enabled, is still a core requirement for innovation. You need control. And the need for robust, well-designed software frameworks like Llama Index or DSpy to manage complexity is as strong as ever.
Same old systems challenges, new context.
Pretty much. The core battle axes for winning in this space remain: total cost of ownership, TCO, dependability, safety, security, reliability, and user experience. Those never go away. Furthermore, wrangling a vast heterogeneity of workloads, each with different performance needs, is a classic systems problem that continues to reemerge, but now with the added complexity of diverse AI models and agent behaviors.
Okay, so lots of familiar challenges.
Yeah.
What about the misconceptions? Where people may be getting it wrong?
Right. Several experts robustly challenge some widely held beliefs floating around the industry. First, the notion that CPUs are dead. Largely incorrect, they argued. CPUs are actually reemerging as incredibly important, especially as agents make more calls to traditional tools, databases, enterprise systems, things that predominantly run on CPUs. The agent's hands often need CPUs.
So the brain might be a GPU, NPU, but the tools still need CPUs.
Often, yes. Second, the singular, almost exclusive focus on pre-training large models. While foundational pre-training is slowing down, partly because we're literally running out of novel, high-quality text data. The emphasis is shifting dramatically to post-training techniques like RLHF and, critically, to inference, making models useful and efficient. Third, the idea that the same infrastructure used for training models will suffice for inference. This is a profound misunderstanding, according to folks like Bill Daly. Inference is a fundamentally different beast. It needs hardware that can be, say, 20x more efficient than training hardware, demanding very low latency and real-time responsiveness. Training can happen offline. Inference is often interactive.
Different jobs need different tools, even at the hardware level.
Absolutely. Fourth, the exclusive focus on developing and deploying only very large monolithic models. Experts predict a strong practical shift towards distilling these large foundation models into smaller, more specialized ones. These are far more efficient and cost-effective for specific agent tasks. Think specialized agent roles. And finally, the belief that basic research is dead and it's all engineering from here on out. This was strongly refuted by multiple experts. There's immense fertile ground for novel research ideas, especially in areas like parallel thinking, like Google's DeepThink, model composition, new framework designs. Basic science is critical to push the frontier further.
Good to hear basic research isn't dead. So based on all these challenges and opportunities, what capabilities do the brightest minds in the field wish agents had today, right now? What would truly revolutionize their potential and unlock that next phase of agentic AI? What's on their collective agentic AI wish list?
The top desires and current limitations are quite clear, and they really highlight where the most significant breakthroughs are still needed. First and foremost, memory management. This came up again and again. It's universally called the most critical unmet need.
Memory, like remembering past conversations.
Exactly, but much more than that. Think about how you operate. You learn from interactions over days, weeks, months. You remember context, preferences, past successes, failures, building this cumulative understanding that informs your future actions. Right now, our agents are largely amnesiac outside their immediate session. They finish a task and poof, it's like hitting a reset button.
Like Dory from Finding Nemo.
Kind of. Experts are clamoring for simple, unopinionated abstractions for context injection and truly long-term memory that can span days, weeks, or even months of interaction. The current reliance on basic search tools as a proxy for memory is just insufficient. It's like asking a human to do their job with perfect Google access but zero personal memory. They'd constantly be relearning everything, unable to build true expertise or personalize interactions.
Right, you need that continuity.
It's the fundamental gateway to truly intelligent, adaptive, and personalized agents. Second, solving hallucinations and improving reliability. This is huge for trust. Agents still confidently state incorrect information, often with absolute conviction.
The confident wrongness problem.
Exactly. A key desire is for models to simply say when they don't know. Instead of fabricating an answer, they should be able to express uncertainty or admit a lack of information. Just say, I don't know, or I'm not sure. The fundamental issue of reliability and consistency remains a massive hurdle, especially impacting trust in critical applications where accuracy is paramount. An example given was a top-tier model hallucinating when asked for the top 10 companies by market cap, even after being explicitly prompted to double-check its sources. Still got it wrong.
Ouch, even when told to check.
Yeah, highlights the inherent difficulty. Third, increased time horizon for coherent reasoning. Current agents struggle to maintain coherent reasoning and follow multi-step plans beyond, say, tens of minutes. They lose the plot. Extending this time horizon is crucial for agents to perform truly complex, multi-step tasks that might take hours or days, and crucially, to self-correct and truly learn about the tools and environments they interact with over extended periods.
They need a longer attention span.
Essentially, yes. Like teaching a new employee a complex workflow, they build understanding over time, not just in short bursts. Agents need that same extended learning capability to be diligent and adaptive. And fourth, better access connectors and identity on the internet. While MCP is a promising step towards standardization, there's a desperate need for more ubiquitous connectors to all third-party services and internal enterprise systems. Agents need ways to interact with everything. A major practical blocker here is what's being called the identity on the internet problem. Simplifying the process of securely giving agents access to personal and corporate accounts without requiring users to navigate dozens of complex and often confusing OAuth flows for every single service.
Logging into everything for the agent must be a nightmare.
It is. This is a very tractable problem that needs industry-wide collaboration, but its solution is critical for agents to truly interact seamlessly with our digital lives.
Okay, memory, reliability, longer reasoning, better access. Those are big hurdles. Now, let's push our imagination forward just 1 year from now. What specific tasks did these experts confidently predict agentic AI will perform better than humans by, say, August of next year? These sound like bold predictions.
They are indeed bold and maybe a little surprising. These predictions offer a glimpse into the very near future, according to the folks at the summit. Coding. Agents are expected to surpass mid-level human engineers in many common coding tasks. Not necessarily groundbreaking architecture, but generating, debugging, refactoring significant chunks of code.
Better than a mid-level engineer in a year. Wow.
That's the prediction. Form filling and manual data entry. Less flashy, maybe, but incredibly impactful. Agents will become demonstrably faster and more accurate than humans for these repetitive, detail-oriented tasks. Huge potential for reducing errors and freeing up human time. Scientific research. In very specific, targeted domains, agents are expected to excel beyond human capabilities. Not broad discovery everywhere, but in areas where large datasets, complex simulations, and iterative experimentation can be automated and optimized by AI.
AI scientists in specific niches.
Exactly. Vision. Despite some current weaknesses in visual language models, VLMs, significant and tractable improvements are expected in the next year. This could lead to human-surpassing performance in various vision-related tasks, from object recognition to complex scene understanding, data analysis, and dashboarding. Agents are already incredibly close to human performance here, rapidly extracting insights, generating visualizations. The experts confidently predict they will surpass human capabilities for many standard data analysis tasks within a year.
Automating the business analyst role.
A lot of it, potentially. And finally, algorithm generation. This one is particularly surprising and profound. For non-trivial problems in complex domains like systems design, networking, databases, agents are expected to be able to generate novel algorithms, solutions that might previously have required PhD-level research.
AI generating novel algorithms. That's something else. It really is. Finally, what invaluable guidance do these pioneering experts offer to the next generation of researchers and engineers, the ones looking to push the frontier of agentic AI? What should they focus on?
Their advice was really insightful and can be synthesized into several key points. Reject conventional wisdom. Don't just aim for incremental improvements on existing ideas. Think from first principles. Question every assumption. Aim for theoretical performance bounds. Imagine how good things could truly be, not just slightly better than they are now. True leaps come from breaking the mold.
Don't just follow the herd.
Exactly. Work on small models. This was a really interesting, pragmatic piece of advice. Instead of only chasing ever larger models, focus on making smaller models achieve the capabilities that currently require much larger ones. This drives efficiency, democratizes access, and can lead to equally profound breakthroughs in understanding intelligence itself. Be a full-stack scientist or engineer. Specialize, yes, but cultivate a broad understanding across the entire stack, from the hardware, low-level software, up through the models, communication protocols, applications, user experience. This holistic view is crucial, especially for debugging these complex agentic systems. The problem could be anywhere.
Know a bit about everything.
You need to. Focus on foundational science. Despite some hype suggesting it's all engineering now, basic research is alive and absolutely critical for true breakthroughs, like parallel reasoning, new architectures, understanding emergence. Don't neglect the fundamentals. And drive horizontal integration. Don't create arbitrary boundaries between domains. Understand how infrastructure choices inherently shape research directions. Recognize, for instance, how memory bandwidth limits might have influenced LLM architectures. A holistic perspective connecting hardware to algorithms to applications will yield the most profound advancements.
What a deep dive. We've journeyed from the raw silicon powering these systems through the intricate frameworks orchestrating their behavior right to the very edge of what's possible with agentic AI. It's clear we're in a period of intense innovation, wrestling with fundamental challenges like reliability and memory, yet seeing these incredible breakthroughs in how agents learn and perform increasingly complex tasks.
Indeed. It's a fascinating, fast-moving field. And if we connect this all back to the bigger picture, it raises an important, maybe even slightly unsettling question for all of us to think about. If a system's reliability fundamentally hinges on clear, explicit specifications, and today's cutting-edge AI agents, particularly the black box LLMs powering them, often inherently lack these clear specs, what fundamental shift in how we design, how we evaluate, and even how we interact with AI will be necessary to fully trust them, especially in critical, automated decisions where we want to move beyond having a human constantly in the loop? This isn't just a question for engineers and researchers, is it? It's a societal one for all of us as we embrace this new era of intelligent autonomy. How do we build trust in systems we don't fully understand?
A truly fascinating thought to mull over as you consider the future of AI. How much transparency do we need for trust? Thank you for joining us on this deep dive. We hope this exploration has given you a powerful shortcut to being well-informed.
This was the Gist Podcast. If you liked it, please leave a like and subscribe to this channel.